Welcome back to round 2 of probability models. Alright, our first vocabulary word is a sample space, and it is the set of all possible outcomes of a random phenomenon. Now you might be wondering, what is a random phenomenon? A random phenomenon could be a coin, and the set of all possible outcomes of a coin, a random phenomenon, would be heads and tails. We could be talking about a die is a random phenomenon, and the set of all possible outcomes would be, well, what numbers could come up on the die? Well, it depends on what type of die we're talking about, but your standard 6-sided die, your sample space would be the numbers 1, 2, 3, 4, 5, 6. Another random phenomenon could be your random number table. It could be a variety of things that are truly random. And all the different outcomes that you could get from your random whatever it may be makes up your sample space. Now, an event is any outcome, or it could be a set of outcomes, multiple outcomes, of a random phenomenon. An event is a subset of the sample space. It's a part of the sample space. So an event, if we were talking about, say, rolling a die, an event could be rolling a 2. It could be rolling a 6. It could be rolling an even number. And an even number is a set of outcomes because we're really talking about 2, 4, or 6. And 2, 4, and 6 are elements of, or events of, the entire sample space. Now, a probability model is what we're going to be focusing on here mostly today. And it is a mathematical description of a random phenomenon that consists of two very important parts. A sample space, so all of your outcomes that you could get, and a probability for each outcome. If you have time to write that down, you could always just pause the video if I'm going too fast. So we're going to look at 3 examples of probability models. The first one, a coin, is our random phenomenon. So our sample space, typically you use the capital letter S for sample space, and we use equals, and then we're going to use our fancy curvy squiggle brackets here to contain all the events of our sample space. So again, our 2 events for tossing a coin are just going to be heads and tails, which I'm just going to refer to as H and T. If you want to actually write the words heads and tails, knock yourself out. But if you want to shorten it down and just abbreviate it, you could certainly do that. Alright, so here is our probability model. We're going to have outcomes going across one row, and the probability for each of those outcomes is going to be tied into the next row. So our 2 outcomes, heads and tails, probability of getting a heads and probability of getting a tails, we're assuming this is a fair coin, is 50-50. Now, you could write the probabilities any way you want to. If you want to use decimals like I did here, that's fine. If you would prefer to use percentages, that is perfectly fine. You could say 50%, 50%. Or if you prefer fractions, you can always go with fractions and say 1/2 and 1/2. Okay, so decimals, fractions, percentages. Any of them are completely acceptable answers. Now for the second example, the sum of 2 die rolls. Okay, so I'm going to roll 2 6-sided die, and I'm going to add together the 2 numbers that I see that come up. Okay, and here are all 36 possibilities here, because I could have all the way from snake eyes all the way to double sixes. So my smallest sum would be 2, my largest sum would be 12, and I could get any number in between. So my sample space is the numbers 2 through 12. And let's put an end squiggle bracket there. So there's my sample space. So now when I go to make my probability model, my outcomes, I'm going to put all of my sample space into those little pieces in there. So there's 2 through 12. Now, is it always true that each of these outcomes has the same probability of occurring, like it did for heads and tails? Not necessarily. Okay? So we just talked about there are 36 total possibilities here. And how many times does a sum of 2 happen? Right there. 1 time. So the probability of rolling a sum of 2 has a probability of 1 out of 36. Because there's the 1 time that it happens. Then if we were to move on and look at, well, how many different ways can a 3 come up? Well, if you see up here, you could roll a 2 and a 1, or a 1 and a 2. And there's no other way to really roll a sum of 3. So there are 2 possibilities out of 36 total. And then for 4, what you might start noticing here is a pattern. So let me re-highlight my 3's, go re-highlight my 2. Now for 4's, I could roll a 3 and a 1. I could roll 2 2's. Now, the reason why there's not another 2 2, because you might be thinking, well, here's a 3 and a 1 and a 1 and a 3. You just flip-flop those. That's true. But a 2 and a 2, if I flip-flop these, it looks exactly the same. So it really only counts as one event. But a 3 and a 1 and a 1 and a 3, they are technically 2 different events. So there are 3 there. And I'm just going to keep continuing on with the pattern here. Here's a 4 and a 1 for a 5, a 3 and a 2 for a 5. Now flip it around, and there's 4. And then for 6's, 5 and a 1, a 4 and a 2, a 3 and a 3, which can't be flipped, a 2 and a 4, and a 1 and a 5. And hopefully by now you're seeing the pattern here. And for 7, this is where we see the maximum occur. That there are 6 possibilities for rolling a 7. A 6 and a 1, a 5 2, 4 3, flip them around, 3 4, 2 5, 1 6. And then all that's going to happen is it's going to start decreasing. There's only 5 ways to roll an 8, 4 ways to roll a 9, 3 ways to roll a 10, 2 ways to roll an 11, and 1 way to roll a 12. So if I finish out my probabilities here, and notice I'm writing them all as fractions. You could write them as decimals or percentages, but they don't work out to be as nice. And there's my full probability model. All right. Now example 3 says, let your pencil point fall blindly into table B, and table B is table D, which is our random number table, and recording the digit it falls on. Well, you got to think about, for your sample space, what numbers could you randomly pick on a random number table? Well, the only digits that were on there were 0 through 9. So there's our sample space, 0 through 9. And what's the probability that you would randomly select a 0, or a 5, or a 2, or an 8, or a 6? Well, they're all randomly the same. So since we have 10 digits here, 10 random digits, and each of them have the same probability of occurring, you have 100% total probability divided by 10 digits, which just means that each has a 10% probability, or as a decimal, 0.1 or 0.1, or you could say as a fraction, 1/10. So I just happen to write them all as decimals. But if you want to write them as percentages, as fractions, it really doesn't matter. Now example 4 is a little bit of a different one, but I wanted to throw it in here. You've got a spinner, and this spinner, the smallest number on it is 0. And it goes by quarters here. Okay? Now it could land anywhere on any decimal in between. I'm not saying that it's always going to be a 2-digit decimal number. It could land on 0.34625874392. Okay, so any decimal between 0 all the way up to this point right here, which we will talk about. So the sample space, we can't really write down what numbers because I'm telling you it could land on any decimal. Well, how many decimal numbers are there between 0 and 1? There's infinitely many. We can't really truly write every number in the sample space. So, in cases like this, which will rarely happen and are more theoretical in nature, we're going to use inequalities. So, when we write this, we're going to say, well, what's the smallest number it could land on? Well, the smallest number it could be is 0. Okay? And we can go bigger than that, and it could be equal to 0 because it's an actual possibility here. So we'll say that the number that we spin, and I'm going to call it x. You can call it whatever you want to. But x, the number I spin, is going to be greater than or equal to at least 0. But what's the maximum it could be? Well, if I told you it went by quarters, you might think, well, it could go all the way up to 1. But 1 doesn't exist. The smallest are really right below the 0 here, to the left of 0. Well, what is the biggest decimal number that's got to be less than 1? You might think, well, that's got to be 0.9 repeating. Okay. Now, I could talk about in class, or I could just kind of blow your mind here and let you think about this. But 0.9 repeating is really equal to 1. And you might think that seems impossible. But I know I've showed this to some of you, especially on the math team. But it is true. Okay. Now, we can't actually reach 1, but we can virtually reach 1. So 1 is kind of the maximum, which we can't truly get to. So we'll just say that the number we spin must be less than 1. It can't equal 1, but we'll just leave it at that. Okay? Even though this little trick is technically true, we'll still say it's technically less than 1. Alright. Let me get this out of the way. There's the more official way. I had it there. Oh, well, I guess I'll go ahead and show this to you. Couple plans to have 3 children, with hopes of having 3 girls. How many outcomes are there in the sample space? And I've already got here 2 to the 3rd power, which is 8. You might wonder, well, how did I come up with 2 to the 3rd power? Well, here's one way you can do some simple kind of combinatorics here. Imagine you're going to have 3 kids. And here's your first child, second child, third child. Well, how many different possibilities could you have for your first child? Well, it's either going to be a boy or a girl, so you have 2 possibilities. And for your second child, does the result of the first child have any impact on the second child? Not really. So how many different possibilities could you have for your second child? Boy or girl. And for your third child? Boy or girl. And in cases like this, you always multiply your probabilities. Okay? Because you're going to have a grand total of 3 kids, and 2 times 2 times 2, a much simpler way of stating that is 2 to the 3rd power, which is 8. So if you're going to have 3 kids, there are 8 possible outcomes that could happen. And so down here we're going to write out what all of those different 8 outcomes are. Now, let's start with what the couple here hopes to have, 3 girls. That is one possibility. So I'll say girl, 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 G, G, G. Now it could be that the first child was not a girl, that it was a boy. And then let's say the next 2 kids are girls. Okay. Now imagine, what if the first kid was a boy, the second 2 were girls, but what if the boy had come as the middle child? And the first and the third were girls. Or we could also think about, what if the boy was the last one? What if you had 2 girls and then finished with a boy? So I thought about all the different outcomes of having 2 girls and a boy. And the boy is either the oldest, the youngest, or the middle child. Okay. Now I can kind of think about, I'm going to go on the opposite extreme here. Instead of having 3 girls, what if we had 3 boys? And now I'm going to do the same thing with what I did here with only having 1 boy. But now I'm going to do it with only having 1 girl. So what if my oldest child was a girl and the other 2 were boys? And now I'm just going to take the girl and say, what if she wasn't the oldest? What if she was the middle child? And she had an older and a younger brother. And again, what if the girl had 2 older, oh, didn't mean to put a comma in there, 2 older brothers, and the girl was the youngest? And there are the 8 total possibilities for having 3 kids. All right, some probability rules. The probability, and we're going to start writing probabilities with a capital P, and usually you're going to write something. It could be, just a letter. So we'll say the probability of event A. What this means is the probability of any event occurring must be in between and including 0 and 1. Either something on the worst case scenario happens 0% of the time, or best case scenario, it happens 100% of the time. And it could happen anywhere in between 0 and 100%. Number 2, if S is the sample space in the probability model, then the probability of anything in your sample space occurring collectively is 100%. So this is like saying the probability that you're going to get a head or a tail in a flip of a coin. Well, those are the only 2 possibilities, so it's going to be 100%. One of those 2 things is going to happen. If we were talking about rolling a 6-sided die, we're saying, well, what's the probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6? It's going to happen, so it's 100%. Number 3, the complement of any event A is the event that A does not occur. Now notice complement isn't the same thing as, oh, you look nice today. Oh, well, thank you for the compliment. It's not C-O-M-P-L-I-M-E-N-T, which that is a complement. Complement in statistics and in probability, there's the E after the L there. Okay, and we're going to write the complement, and it kind of looks like we're going to use an exponent that's a C. So if we have event A and we say, well, if event A does not occur, then we say A complement. Okay, kind of looks like A to the C power. And the complement rule states that the probability that A happens plus the probability that A doesn't happen is 100%. So let me put it this way. Let's say A is the event that it rains. So A complement is the event that it's not going to rain. So basically I'm saying with the complement rule is the probability that it rains or it doesn't rain is 100%. Because one of those 2 things is going to happen. It's either going to rain or it's not going to rain, which collectively is 100%. Now they have individual probabilities tied to them, but together it makes 100%. Now complementary events are 2 disjoint events whose union is the sample space. Okay? What I mean by union is kind of a collective. If you look in your picture here of this Venn diagram, it isn't your typical Venn diagram, but it is kind of a Venn diagram in here. That here's event A, and here's event A complement. Okay, so here's event A happens. Everything that falls outside of A is A complement. Okay, so when you look at both of these things grouped together, it makes up your entire sample space. Okay, the probability of anything happening within this rectangle is 100%. It's either going to land in A or it's not going to land in A, an A complement. So if we had A plus A complement, up here I said that is 1 or 100%. Now some of you might have seen this symbol here. Kind of looks like a U. Okay, and we're saying A union A complement. And again, union pretty much means to put together, to kind of combine together. So if you had event A unioned with things that are not in A, that is your sample space, which is what I just mentioned up here, whose union is the sample space. I just basically wrote that mathematically. A union A complement equals your sample space. Now an upside down U, like this right here. This is what's called an intersect. And it's just saying, what do these 2 things have in common with each other? What do A and A complement have in common? They have absolutely nothing in common. So how do you say nothing mathematically? You might say, well, we can just say 0. 0's nothing. But 0 is an actual event that could happen, in certain sample spaces and certain random phenomena. We could talk about, having, let's see how we put it. If you're going to have 3 children, the number of children that are girls. Well, there is the probability that you could have 3 boys. And how many girls would you have? 0. And 0 could be an actual event in your sample space. So 0 is something. So how do you write nothing mathematically without saying 0 and without writing the word nothing? We're going to use the term the empty set. Okay, the empty set means truly nothing. It basically looks like a 0 with a line slashed diagonally through it. Okay, so basically 0, and basically you're saying nothing. That is called the empty set, the null set. So the empty set, or it is referred to as the null set. There is nothing in it. There is nothing in common between A and A complement. Now, 2 events A and B are disjoint, and we set up here that complementary events are disjoint. Well, what if we had 2 events that wasn't like A and A complement, or B and B complement? So we have 2 events, A and B, that aren't related necessarily in any way, but they are disjoint if they have no outcomes in common. They can never occur simultaneously. If A and B are disjoint, then the probability that A happens or B happens is equal to the sum of their individual probabilities. And this is called the addition rule for disjoint events. Okay, so if you look at your picture down here, this rectangle represents our S, our sample space. Anything that can happen will happen inside of this rectangle. Here we have A. This is event A, whatever event A may be. Here is event B. And everything that falls outside of A and outside of B is not A or B. Or you could say A or B complement. Okay? So again, disjoint events have no outcomes in common. How does A interact with B? Is there any kind of overlap in here? There's not. So anytime you see a Venn diagram and there is no overlap between 2 events, then they are disjoint events because they have no outcomes in common. The event A union B is another way to say A or B. And if A and B are disjoint, then again their intersection, what do they have in common, is the null set or the empty set. Alright, select a woman at random, age 25 to 29 years old, and record her marital status. The probability of any marital status is the proportion of all women aged 25 to 29 who have that status. Here is the probability model. Okay, so here's our sample space. Women have never been married. They could currently be married. They could have been married but now they're widowed, or they could have been married, now they're divorced. Okay, so here is our sample space. There's no other possibility for marital status. All right. So it says, is probability rule 1 and 2 satisfied? Well, if I go back to here, probability rule 1 was that each probability is somewhere in between and including 0 and 100%. And probability rule number 2 is that all of the outcomes together add up to be 1. So let's see. Is each of these individual probabilities in between 0 and 1? Yes. Now for rule number 2, I've already got yes that it's satisfied, but let me show you. Let's bring up the calculator. So the probability of having never been married, 0.353. We add that to the probability of being married, 0.574. Add to it probability of being widowed, 0.002. And the probability of being divorced, 0.071. So the probability of my sample space, which are my individual events, all adds up to be 100%. There's nothing that's being left out. What is the probability that a randomly selected woman is not married? Okay, well, let's see. Here's married, so not married must mean the 0.353. But widowed people aren't married. Divorced people aren't married. So we could do one of two things here. We could say, well, let's take these three sets of women and let's add them all together. Okay, so let's take 0.353. So there's our never married people, our widowed people, 0.002, and our divorced people, 0.071. So there's a 42.6% chance that we randomly select a woman that is not married. Now, most of the time that's what you guys are going to do. You're going to add together all the different outcomes that meets that criteria. Another thing you could do is look at this. If you want to know the probability that a randomly selected woman is not married, well, women who are married is 0.7 or 0.574. Now, what did all of these probabilities add up to be? 100%. So what if I just took my 100% and subtracted away the one type of woman I wasn't concerned about, the married women? So if I subtracted away 57.4% from everyone, what's left over? 42.6%, which is the same thing as adding together the individual probabilities. Now, sometimes this is definitely going to be a time saver. It's not always going to be a time saver, only if you're talking about a very large sample size. Okay, and we will definitely use what's called the complement rule. Okay, the reason why it's called the complement rule is because we were talking about an event, married, but we were talking about the complement of that event, not married. Okay, and so we would take 100%, which is everyone, and subtract away the one event we did not want to happen, and that was married people. And whoever's left over are not married, which counts for 3 different events. But all 3 of these types of women are not married. Find the probability that a randomly selected woman has never been married or is divorced. Now, can there be a woman who has never been married and is currently divorced? Does that make any sense? And you might first think, well, yeah, maybe. But a person who is divorced has been married. So if you have a person that has never been married and a person who was once married, you cannot find a woman that meets both of those criteria. And that's something we'll talk about later on in the chapter. Okay, we'll talk about there are times where a person could be in both of these categories. And then what do you do with that? Because technically you've counted them twice. But again, you cannot have a woman that has never been married and has been divorced. Okay? So we just need to look at never been married, 0.353, and divorced, 0.071. Now these two events are disjoint. They have nothing in common. You cannot be divorced and have never been married, as we mentioned. So we talked about on the previous slide that if you have disjoint events, you are allowed to just add together their probabilities. And that's how I got this 0.424, is by taking my 0.353 plus my 0.071. Together, that gives me my 42.4%. And this was from the addition rule for disjoint events. Now you might be asking, do we need to know the names of these types of rules? No. The one rule that I will use by name a lot of the times will be the complement rule. But again, you're not going to have to know the names of these things. What is the name for 2 events that have no outcomes in common? I just mentioned that was the D word, which is right here, disjoint events.